Hello everyone. So in this lecture, we are going to start studying and working on laminar and turbulent flows, especially in the context of pipe flows. So first, I will define what is the difference between a laminar and a turbulent flow, and after that, we are going to derive and estimate the pressure drop in a horizontal pipe with a laminar flow, and finally, we will estimate a similar relationship for a turbulent flow in a pipe. And so basically, turbulent flows are more complicated and complex than laminar flows because they are more chaotic and they typically have a much higher speed than laminar flows. So laminar flows are typically have low speed, and friction forces are more like the viscous friction forces. Viscous forces are more important in laminar flows and are stronger in laminar flows, while in turbulent flows you have what we call turbulent friction, which kind of acts and tries to mix the flow and make it much more chaotic. Okay, so you may have heard turbulence. It's a common word you may have heard in, for example, when you fly with an airplane, where you see those chaotic and sudden and random kind of sudden movement of air. Those are called like turbulent movements, and this is the same concept that we are studying here, which is about turbulence in other kind of fluids. So it doesn't matter if it is air or water. In all fluids we have these turbulent, we can have these turbulent behavior. Okay, so let's get started with some brief and preliminary definitions. So the flow of a fluid in a pipe might be laminar or turbulent. Here we focus in this chapter on pipe flows, but again, this is also valid for all the fluids and all the flows in open channel flows, air flows, atmospheric flows, oceanic flows. All of them will have the same principle for laminar or turbulent regimes. And so for small enough flow rates, for small enough flow rates, the die streak, if you let a die in a like a fluid that is moving, the die streak, if you release it, will remain as a well-defined line as it flows along. Okay, so if you have small enough flow rates and then you release a die streak in a pipe, it will remain as a well-defined line as it flows along. Okay, so let me say and show this more clearly here. So imagine we have a pipe here, okay, and then we release say a die here, at this point A. So if your flow rate is small enough, what happens is that you see that this streak, the streak, looks like a well-defined line, like something like this. Okay, let me show it here. Okay, so I'm gonna continue this, but this is what we call a laminar flow, because we have this well-defined line here. But for large enough flow rates, the dye streak almost immediately becomes blurred and spreads across the pipe, the entire pipe, in a chaotic fashion. Chaotic fashion. So if your flow rate is very large, okay, so let me show this with another color. So say this is our first, and then if we increase this flow rate a lot, what you see is that this is gonna do some chaotic motion, and it's gonna kind of blur and spread across the whole pipe. Okay, so let me show it again. Maybe this is like it can go here, and then it can have a completely chaotic behavior. Okay, so this type of flows, we call them turbulent. Okay, so let me make a more formal definition of this. So say we have velocity at point A versus time. You can also look at it from the velocities perspective. It's almost similar. So here, say we have the velocity of point A, and then here we have time. So what happens when your velocity is small? Then this velocity is gonna stay constant. It's not gonna vary in time, and the dye streak is also gonna have a well-defined line. Okay, so the velocity looks like a constant line. It doesn't change in time. So this type of flow, we call it a laminar flow. Okay, and when the flow is the velocity is very high, this flow rate is very high, this as you see, the flow starts doing some random and kind of chaotic motion. So the velocity at this point is gonna be also chaotic, right? So if you have like, this is the velocity vector, this can go anywhere, right? This can, if you just look at the horizontal velocity, this can go like here, then here, then here. So this is gonna have a chaotic motion, right? So at one time, you see this is gonna be how the dye is spreading, and then sometime at another snapshot, if you look at it, you will see that the dye is spreading like this. So the velocity at this point is gonna also vary a lot if you have a kind of chaotic motion or a turbulent flow, turbulent motion, okay? So for a turbulent flow, the initial velocity is higher, but it is also chaotic. So we have like some chaotic behavior. So for this, we call this turbulent. And in between these two limits, we have something, a transitional period where we go from laminar to turbulent, okay? So the velocity, if the velocity is somewhere in between those two, then we have like kind of a transitional period where we see some kind of chaotic motion, but they are kind of damped and they get back to a normal laminar flow. So this is what we see in a transitional regime or transitional state, okay? So as you see, we can define these three regimes for in any fluid flow. So a laminar flow where the velocity is not varying with time, is kind of constant at any point in the flow that you look at. Transitional state where we have some motions, like we have some chaotic motions, but they get back to a laminar state, they get damped. And then we have a turbulent motion, which is fully turbulent and fully chaotic, right? So even here, let me make it more clear. We don't have any laminarity here. Everything is kind of turbulent. So we have like this. Okay. So this is the turbulent flow regime. And now what I want to do next is I want to find the pressure drop in a pipe flow for different regimes. First, I will look at laminar flow, which is a simpler case, and then we will look at the turbulent flow. But as you see, the turbulent flow is very complex, it's very chaotic. We don't have any analytical solution for that. So what I want to use is the Buckingham-Pi theorem to be able to find a dimensional analysis. So we can use that dimensional analysis and account for different parameters in the flow and configuration of this problem for finding the pressure drop in a turbulent pipe flow. Okay, so let's get started with the first scenario, which is a laminar flow. So we have let's say laminar pipe flow. Okay. So we want to estimate, let's estimate the pressure drop in a horizontal pipe with a laminar flow. Okay. So here we have a pipe. So here is section 1 and here is section 2. So it has a diameter d and a length L. And then the velocity of the fluid and pipe is V, and it has a viscosity of mu. Okay. So I'm going to use Buckingham-Pi theorem and again that dimensional analysis to find what are the important parameters here, okay, that we need to be careful about to find the velocity in a laminar flow. So pressure drop in this fluid is from P1 minus P2. I want to see how much of the pressure is dropped because of the, say, this viscosity here, right? Because of the viscous friction at the boundaries of the pipe. Okay, so that is my first thing that I want to find. Say, so pressure drop due to viscosity. Okay, viscosity, and so for this, I want to find, write a general function, so list all the relevant variables here. So first, I want to write the dimension of the pipe. So it really depends on the length of the pipe, which is important, right? If your length is higher, your pressure drop is going to be higher. The diameter of the pipe is also another important factor. And also the velocity of the fluid is also very important. And finally, the viscosity of the fluid, right? So this mu is viscosity of the fluid. So based on the steps we learned in the Buckingham-Pi theorem, we have three reference variables. Which are M, L, T. And then based on Buckingham-Pi theorem, we have 5 variables: 1, 2, 3, 4, and 5. And then 3 reference variables. So we are going to have 5 minus 3 equals to 2 dimensionless groups from Buckingham-Pi theorem. Okay? So, we previously found, so I'm not going to go through that steps again because you can do that yourself, but let me see if I have it here. So I just want to write the final thing here. So for delta P, if you do that, for delta P, if you non-dimensionalize it, you will find it's going to be delta P times D over mu V. Okay. So let me write it here. Follow previous steps. Previously learned steps. this is going to be a function phi of the second variable, which is L over D. So here I have chosen D, mu, and V as my repeating variables. So these are my repeating variables. And delta P and L as non-repeating variables. Okay, so if you do that, you're going to get something like this, according to the Buckingham-Pi theorem. And then we make another assumption for pressure drop. Okay, so a second assumption. So a second assumption is that, as you imagine, right, it's completely something you expect, that the pressure drop here should be proportional to the pipe length, right? If your pipe is longer, your pressure drop from this section to this section should be also larger, right? So this is what we expect. It's a physical assumption, it makes sense. And if your pipe is shorter, then your pressure drop should be also smaller. So this is what we expect from physical intuition. And so we make this assumption. So a second assumption we make is that pressure drop is proportional to pipe length. And so I can write that delta P over mu V over D equals to, they are proportional to each other, LD, and then I write C as a constant of proportionality times L over D. I assume that this relation between them is linear. They are proportional linearly. Okay, so C, a constant of proportionality, a constant of proportionality. Okay, so this gives me that delta P over L is gonna be C mu V over D square. Okay, so the pressure drop per length is gonna be C mu V over D square. Okay, so now I want to find this C, this constant of proportionality, for a round pipe, okay? So let's do that and see what is the exact value of this constant of proportionality for a round pipe, okay? So let's find C for a round pipe. Okay. So for a round pipe, we have, if I want to show all the stresses that act on a round pipe, is as follows. So let me show it. So say we have a pipe here. It has a length of L and a radius of R. So, what are the forces that act on this pipe with length L and radius R, a round pipe? So first, here we have pressure at point 1. So if this is point 1, and this is section 2, and then times A, right? So times A1. And because this is a round pipe, so A is gonna be, area is gonna be pi r square, right? So we have pi 1 pi r square. And then here we have the force, another force, which is pi 2 times pi square, or pi 1 minus the pressure drop times pi r square. Remember that P that we had it before from here, that delta P is P1 minus P2. It's P1 minus P2, right? So P2 is P1 minus delta P. Okay? So this is another force we have here. And then we have all the shear stresses that act on the surface of the pipe. Okay? So what is that gonna be? So say if you have one circle, let me show it here. And this has a radius r, okay? So the shear stress, the total shear stress along this pipe is gonna be what? If you have this shear stress, small shear stress here as tau, and then small tau here, so it's gonna be tau times 2 pi r, right? The circumference of this, right? And so this is going to be the total shear stress at one section, and then you have to multiply it by the lengths to get the total shear stress here at all this section here and here, right? So the total shear stress is going to be tau 2 pi r times L. Okay, so this is going to be shear stress. Total shear stress. Let me write it down. Total shear stress. And remember, tau is force per area. So if you want to get the force, the total shear force is going to be tau times area. And we have here also the area, right? This is going to be area, so r squared. So these are the things you should remember in mind, okay, as side notes. So these are side notes. Okay, so this is the free body diagram of this. And now I want to write the forces that act on this. So some of the forces here should be 0. So P1 times pi r squared, if we have this is our x and z, P1 times pi r squared minus P1 minus delta P pi r squared equals to tau 2 pi r L. Okay, so this is going to be the sum of the forces. Okay, and these two terms are going to cancel out. So this pi 1 and this is going to cancel out. So I'm going to only have delta P pi r squared equals to tau 2 pi r L. And again, pi r is going to cancel out. So here I only have r. And so this gives me that delta P over L is 2 tau over R. Okay? Interesting, because this is getting closer to this form that we want, but we need to find this tau, which is the shear stress that acts, the fluid acts, applies to the pipe. So for a Newtonian fluid, we have tau equals to minus mu du over dr for laminar Newtonian fluid, and we know this from the first chapter. And so I can write delta P over L is minus 2 mu over R du over dr. And therefore, du over dr is going to be minus delta P over 2 mu L times R. And now if I rearrange the terms, I get du equals to minus delta P over 2 mu L R dr. And so I can integrate this. I can integrate this to get u, the velocity distribution of u. Okay, so if you integrate this, we are going to have the left one, the integral of du is going to be just u, so ur equals to the integral of the second term, so this is constant, I can take it out of the integral, and then the integral of r dr is going to be r squared over 2. Okay, so for those who might have forgotten the calculus, the integral of r dr is going to be r squared over 2 plus c, which is the constant of integration. So here we have the same thing. We are going to have delta P over 4 mu L r squared plus c1, which is the constant of integration. So this is constant of integration. Again, this is a side note. And so now I can calculate the whole Q, which is what? Which is the flow rate here. It's gonna be U times dA. Okay. So what I'm gonna do is say I want to find, so this is the UR, which shows the velocity distribution with respect to radius. Okay, so if I have, say, this circle here, okay, and this is my R, right? This is, say, R, and this is capital R, the whole radius of the flow. So let me, of the pipe, so let me write it with capital R, because this is the whole radius. So for a small, I want to calculate the total flow rate that is going around this. So what I want to do is I want to calculate first U at here, and then I want to take kind of an element here which has dr, which has a length of dr, Okay, so this has a length of dr. Okay, and then I want to calculate the total flow rate by integrating the velocity at this section. Say if this has a velocity ur. Okay, so I want to calculate the velocity at this section. So let me do it this way. Make the opacity lower a little bit. So I want to calculate the flow rate that is passing through this small element that I have shown here. Okay. So say here this small element has a velocity of ur. Okay, so the total flow rate, the flow rate that goes out of that is what? So if we have this, it has like a dq, say the dq, the flow rate of this dq is gonna be, the flow rate is what? Flow rate is velocity times area, right? Times area, VA or UA. Okay, so dq is gonna be u at r times dA. Okay, the area of this, which is shown with this blue color. Okay, so now I want to find the total flow rate, so I have to integrate over the whole domain. So all of these small dq's from 0 to r, which is going to be the integral of 0 to r of ur times dA. Okay, and what is dA? Let's now calculate dA. So dA, if I want to spread this, let's say I want to spread it, what I'm going to have, if I spread it and on a surface, so I have something like this. It will be like a rectangle. It's a small thing, so I can just assume that this is still gonna remain as dr. This length is dr, and this length is what? This length is, can you guess what is this length if you spread this down? So until you think, I will just color it again. What should be this length be? This length should be the circumference, right, of this circle, which is going to be 2πr, right? So this is the length of that. If you spread that, so spread it, open it or spread it, and so the area of this is going to be, this dA is going to be what? If this is like a rectangle, so I can say this is, the area is going to be 2πr times dr, right? This is like a rectangle. A rectangle. So this gives me a formula for here that I can use here. So this is going to be the integral from 0 to r of ur 2 pi r. So from for dA, I write it from here, 2 pi r times dr. Okay. So if you calculate this integral, and I'm not going to calculate it, this is something you can calculate yourself, or you don't need to calculate it. There are some tables for this integral, but you can take this integral. So take this integral, and the answer will be q equals to and instead of you should put this here. Okay, so let me say take this integral. What is the integral? It is integral from 0 to r of minus delta p over 4 mu l r square times 2 pi r dr. And taking this integral, this might be a little bit difficult, but you can take it simply. And what you will get is q is delta pi over times pi, the d to the power 4, d is the pipe diameter, 128 mu l. So d is pipe diameter, which is 2r. So this is going to give me, the total flow rate is going to be like this for a circular round pipe. Okay? And I know that v, the velocity, is nothing other than q over a, or flow rate is v times a, we know that. So velocity is going to be q over the area for a pipe is p pi d square over 4, which is going to give me from this formula, if you calculate it, it's going to give me delta p d square over 32 mu l. Okay. So interestingly, you get that delta p over l is what? It's 32 mu v over d square. What does this remind to you? What does this remind you? Look at here what we got from the dimensional analysis. We got this formula. Let me copy it here so you can compare it. Very interesting. It's very similar to this one, and the only difference is we didn't know C, but here we were able to find C for a round pipe. But by what? By just using the sigma f equals to 0, which is the Newton's second law, and tau equals mu du over dr for a laminar Newtonian fluid, and also some integration. We were able to find this C. So we found this C for round pipes. This equals to 32. Okay. Now I want to further simplify this relation. So delta P, we found that delta P in round pipes is, for laminar flows, is delta P is 32 mu V L over D square. So I divide this by the whole thing by 1/2 rho V square, which is dynamic pressure. We call this dynamic pressure. If you look at also the definition of Bernoulli equation, this was one of the interpretations of this term, which is dynamic pressure. So if you divide everything by that, we get delta P over 1/2 rho V square equals to 32 mu V L over 1/2 rho V square, which equals to 64 times mu over rho V D times L over D. So this is very interesting formula. Why? Look at what we had before. What it is. Very interesting. Look at this number. It's rho VL over mu. It's Reynolds number that we learned before. Rho VL over mu. Here we have the similar thing, rho VD over mu. So this is 1 over Reynolds number, right? We have mu over rho VD. Rho VD over mu is known as Reynolds number. So this is just 1 over Reynolds number. So this equals to 64 over Reynolds number times L over D. So we found that delta P is 64 over Reynolds number times L over D times 1/2 rho V square. Or a general formula, I can write this instead of this. 64 over Reynolds number, I define delta P equals to F, which is we call it friction factor, times L over D times 1/2 rho, or say rho V square over 2. This is a very general formula for laminar flows. So F is friction factor. And we found that for friction factor, for laminar, fully developed round pipe flow is 64 over Reynolds number. Very interesting formula. So this gives us the pressure drop in a pipe flow that we can find for a laminar flow. It's only a function of Reynolds number. But later on, for turbulent flows, we will see that not only it's going to be a function of Reynolds number, but also other parameters like the roughness of the pipe and inertia are going to be also important for turbulent flows, right? So here is a simpler case, which is for laminar flows. And in the next lecture, we will go through the pipes for turbulent flows. And those are more commonly used pipes in engineering applications. We don't typically have laminar flows. Usually the flows are high that might lead to turbulence. But also sometimes we want to actually design pipes that are in a laminar regime to decrease friction in the system. Okay, so let's briefly overview and review what we learned today. So we started with laminar or turbulent flow. We defined the definition of laminar versus turbulent. So laminar is the one when you release a die, the streak is kind of flows along a well-defined line, and also the velocity is going to be constant in time at one point. And then in a flow, but for turbulent flows, you have like chaotic motions, and the velocity at one point can be chaotic and change kind of chaotically, okay? And then we estimated the pressure drop in a horizontal pipe flow with a laminar flow. So we did that first by using the Buckingham-Pi theorem. We got this formula. Okay, so we got this formula by using Buckingham-Pi theorem. And then we had a constant of proportionality. Also the pressure, this assumption that the pressure drop is a function of pipe length. We found that. And then we found the C for a round pipe by using the force, the sum of the forces should be 0 because there is no acceleration here in the whole system. And also we use this tau equals to mu du over dr for a laminar Newtonian fluid. And then we got to this integral, and then we solved this integral. And after solving this integral, taking this integral, you will get this, the total flow rate versus the delta P. And finally, if you calculate everything, this is going to be the delta P over L, and this gives me the C of 32, which is a constant of proportionality for a round pipe with a laminar flow. And then if you divide everything by 1/2 rho v square, finally you get to this equation. Or in a general form, the pressure drop in a pipe flow is going to be F times L over D times rho v square over 2, where F is called friction factor. And for a round pipe with laminar fully developed flow, the friction factor is going to be 64 over Reynolds number. And we are going to look at turbulent flows in the next lecture. Thank you very much, everyone.